this video, we will see how EMS can be used to study sensing coils. In this model, we have two coils. We have the lower coil and the upper coil. We also have a plunger that at its initial position is shown here. As the plunger moves up, it comes in the vicinity of the two coils, and the voltage and the current measured in the coil determines the position of the plunger as well as the speed of the plunger. So in this example, we will see how EMS for SolidWorks using the transient magnetic simulation will help us understand what's the current in both these sensing coils as the plunger moves up. So we start off with creating a transient magnetic study. Now this transient magnetic study is coupled to a SolidWorks motion study. This enables us to impart motion to the plunger. Let us now take a look at the SolidWorks motion study to understand what kind of motion is given to the plunger. So the plunger actually starts from rest and it's at its current position for a period of about 0.02 seconds or 20 milliseconds. Now from a time of 20 milliseconds to 40 milliseconds, the plunger moves 4 inches. Okay? And finally, from 40 to 80 milliseconds, the plunger stays at its position, which is the topmost position. Now let us look at the materials. The coils, obviously, both the lower as well as the upper coil, they are made of copper. EMS has its own material library which contains a plethora of commonly used materials in the field of electromagnetics. This material library is fully customizable, so users can actually create their own materials and use them for simulation. Now let us take a look at the definition of the coils. We'll start with the lower coil. The lower coil is actually excited using a AC voltage source. Now it has a frequency of 50 Hz and the amplitude of the AC voltage is 40 volts. The coil also contains 300 turns of 22 gauge copper. A similar coil is applied to the top coil as well because they are similar in dimensions. It contains 22 gauge copper, 300 turns, and it is excited with the AC voltage of 50 Hz with the amplitude of 40 volts. So this completes the setup of the problem. Now we have solved this problem and I will jump straight into the results. The results are organized in EMS in what we call as the result table. In the result table, one can study the motion of the plunger. For example, here is a plot of the center of mass of the plunger, and that mirrors what we applied as motion. For the first 20 milliseconds, the plunger is stationary. That helps us to understand the amplitude and frequency of the current. And during the motion from 20 to 40 milliseconds, the plunger is in a uniform motion. And finally, from 40 to 80 milliseconds, it stays at its topmost close position at rest. One can measure the current, which is the most useful thing as far as characterizing the sensing mechanism is concerned. So here is a plot of the currents in both the lower as well as the upper coil. Now, as you notice in this plot that when the plunger is at the lowermost position up to 20 milliseconds, the current, the amplitude as well as the frequency of current in both the coils are almost exactly similar. But as the plunger starts moving up, you see a difference between the lower coil as well as the upper coil. The blue is the current distribution in the lower coil and the red line is the current distribution in the upper coil. So you can see that Once the plunger is in motion, the magnitude of the current in the lower coil drops first, and then the magnitude of the current in the upper coil drops next. And once the plunger is in a completely closed position at its topmost position, you can see again a lower magnitude current, but almost very similar ones between the upper and the lower coil. By studying this current, one can characterize the sensing coils, and one can also understand what would be the location of the plunger as well as the speed of the plunger. We can also study other things. For example, the self-inductance of the two coils as well as the mutual inductance, they can be studied. And here is a plot of the self-inductance of the two coils as well as the mutual inductance, which is shown in red. So we can see and study the inductance of these coils as a function of time. The inductance also helps us to understand both the motion as well as the position of the plunger. Also, the induced voltage can be studied. So the induced voltage in both these coils are now plotted, and you can see how the induced voltage in both the coils vary as a function of time. Okay. So the applied voltage was 40 volt and 50 hertz frequency, and you can see what's the induced voltage in the two coils. Since we are inside the SolidWorks motion environment, we can also visualize the motion. This is the motion of the plunger, and we also saw in the results table how the current, inductance, induced voltage, etc. vary as the plunger moves from its rest position to its topmost position. Thank you for watching this video. As a recap, in this video, we saw how EMS for SolidWorks can be used to study the characteristics of sensing coils. For more information, please visit our website. Thank you.